Hello, I'm Alex Sanchez, and today we're going to talk about some of the advanced features and parameters in HEC-RAS. In this short video, I'm going to cover three topics: turbulence, Coriolis, and matrix solvers. For each of these, I'll give a brief overview of the theory and numerical implementation. I'll show examples for turbulence and matrix solvers, and I'll cover some guidance and best practices for all three topics. A lot of the material covered here is described in detail in the hydraulic reference manual and also the user's manual. These documents are available from the HEC-RAS website or the HEC-RAS help menu. Turbulence is a type of fluid motion which is unsteady, irregular in space and time, dissipative, and diffusive. Turbulence modeling is the process of representing or simulating the turbulent effects within flows using mathematical and empirical equations. Most natural flows are turbulent. In addition, the current velocities are both depth averaged and horizontally averaged along faces. The non-uniform velocity distributions in the vertical and horizontal lead to momentum dispersion. Both turbulence and dispersion are modeled within HEC-RAS as a diffusion term within the momentum equations. There are aspects here that sometimes get confused. One is the formulation of the momentum diffusion term within the shallow water equations, and the other is how the eddy viscosity is calculated. This is referred to as the turbulence model. Both of these aspects have changed and are improved in version 6.0. HEC-RAS has two formulations for the diffusion term, also known as the mixing term. The non-conservative formulation was the only option in versions 5.07 and earlier, but is still an option in 6.0. It computes the Laplacian of the velocity field times the eddy viscosity. For many natural flows, the Laplacian tends to be on average negative, and this results in a net dissipation, which is not great because it can start to increase water levels, and then in order to calibrate, the bottom roughness has to be adjusted to compensate. This is why a new conservative formulation has been developed. It's the default in version 6.0 and is the only option for the Eulerian shallow water equation solver. It computes the divergence of the diffusive fluxes, and for this reason it's more conservative. This slide shows a comparison of the two mixing term formulations for a simple parabolic channel. The top plot shows the bathymetry and water level. The middle plot shows the velocity with the non-conservative formulation in black. The blue line represents the velocity profile without mixing, so only based on conveyance. Because the velocity curvature is negative everywhere, the mixing term results in a net dissipation and lower velocities. The bottom plot shows the velocity profile with the conservative formulation also in black, and the blue line also representing the velocity without mixing for comparison. There, the velocities are decreased along the center of the channel and increased along the sides, which is much more realistic. This simple example clearly illustrates the problem with the non-conservative formulation. One significant improvement in HEC-RAS 6.0 is the addition of a new turbulence model. In versions 5.07 and earlier, the eddy viscosity was computed with a simple isotropic parabolic model. It has one parameter, the mixing coefficient d. In version 6.0, there is a new formulation which is a combined parabolic Smagorinsky model. It has a non-isotropic mixing coefficient and an additional Smagorinsky term, which is a function of the horizontal velocity gradients. This is important because areas with high horizontal shears produce more turbulence. The new turbulence model is better, but it's more computationally expensive because of the velocity gradients. It also has three parameters instead of one, so it can be more difficult to calibrate. However, it does generally produce better results. The three parameters are the longitudinal and transverse mixing coefficients and the Smagorinsky coefficient. If the longitudinal and transverse mixing coefficients are set to the same value, and the Smagorinsky coefficient is set to 0, then it reduces to the previous formulation. The Smagorinsky model is sometimes criticized because it tends to underpredict the eddy viscosity in fine resolution areas. However, this model doesn't have that problem because of the first term. The first term represents the turbulence produced by bottom friction and dispersion, whereas the second term represents the turbulence produced by subgrid flows and horizontal shear. Both of these formulations are referred to as zero-equation turbulence models, and they offer a good compromise between accuracy and computational time. The HEC-RAS turbulence parameters are set within the unsteady flow analysis editor. This can be opened from the main RAS window by selecting the button that looks like a stick figure running up a hill. Then from the Options menu, select Computation Options and Tolerances. Then navigate to the tab called 2D Flow Options. The turbulence parameters begin on line 10 with Turbulence Model, which is actually the mixing term formulation. This can be set to non-conservative or non-conservative, which is the original formulation in HEC-RAS 5.07. The longitudinal, transverse, and Smagorinsky coefficients are lines 11, 12, and 13. All of the turbulence parameters are plan and 2D area specific. In this case, the 2D area is called Flume. In order to understand the strengths and limitations of the different formulations and solvers, it's important to understand some basic aspects of the numerical implementations. The non-conservative form of mixing remains largely the same in 6.0 except for the eddy viscosity. The mixing term is Eulerian-Lagrangian. The eddy viscosity is computed at the phase while the velocity Laplacian is backtracked. Through testing, this was found to have better convergence properties than a full Lagrangian approach. The non-conservative formulation of mixing is not available with the Eulerian solver. The conservative mixing term is available with both the Eulerian and the Eulerian-Lagrangian solvers. In both cases, the mixing term is discretized the same. However, in the ELM solver, the term is backtracked. This means it's interpolated at the backtracking location X. Okay, now I'm going to show some results for an example Flume experiment of a sudden expansion. The purpose is to compare the two flow solvers and the mixing term formulations. The flow is from left to right and was run until steady state. The flow forms a recirculation zone after the sudden expansion, and for this reason it's a great test case for turbulence modeling. It also has a good amount of velocity measurements, which were taken along 6 transects spaced 1 meter apart starting at the expansion. This slide shows a comparison of the current velocity fields for the sudden expansion lab experiment computed with both the ELM and EM solvers and the two mixing term formulations. The top two results are the EM solvers with the non-conservative mixing formulations, and the bottom result is for the EM solver, which only uses the conservative mixing formulation. The first thing to notice is that the ELM and EM solvers produce essentially the same result with the same turbulence setup, which indicates that the flow results are not sensitive to the solver. However, comparing the two mixing term formulations, the results are very different. So different, in fact, that the mixing term coefficients have to be calibrated independently. The calibrated values of the turbulence coefficients are shown on the right. The conservative mixing formulation produces a very weak return flow. For many lab-scale test cases, the resolution can be so small that the stability criteria for the diffusion term of the EM solver can start to become important. This was precisely the case for this test case, and is why the time step had to be reduced for the EM solver. The larger time step is one of the reasons, the smaller time step is one of the reasons why the EM solver was the slowest of the 3 runs. Since the ELM solvers use semi-Lagrangian and Lagrangian approaches for the mixing term, it doesn't have the same time step restriction as the EM solver, and it can use a bigger time step. Of the 3 simulations, the ELM solver with the conservative mixing term was the fastest, beating the non-conservative formulation just slightly. This slide shows a comparison of measured and computed current velocities along the 6 transects of the sudden expansion experiment. In general, the conservative mixing formulation does a better job in reproducing the velocities, especially the return flow, which is most visible in the lower left figure. The EM solver does have a time step limitation from the mixing term. However, for most practical applications, the CFL condition is more restrictive. Currently, the variable time step algorithm in HEC-RAS does not check the diffusion stability criteria. This is something that could be added in the future as an option. The ELM solver does not have a time step restriction based on the mixing term because it is treated with the Lagrangian approach. And finally, the EM and ELM solvers should produce similar results for the same turbulence coefficients. The HEC-RAS turbulence parameters are set within the unsteady flow analysis editor. This can be opened from the main RAS window by selecting the button that looks like a stick figure running up a hill. Then from the Options menu, select Computation Options and Tolerances. Then navigate to the tab called 2D Flow Options. The turbulence parameters begin on line 10 with Turbulence Model, which is actually the mixing term formulation. This can be set to none, conservative, or non-conservative, which is the original formulation in HEC-RAS 5.07. The longitudinal, transverse, and Smagorinsky coefficients are lines 11, 12, and 13. All of the turbulence parameters are plan and 2D area specific. In this case, the 2D area is called Flume. The Coriolis acceleration is a result of the Earth's rotation. It conserves angular momentum within the rotating reference frame of the Earth. It's the reason why storms spin counterclockwise in the northern hemisphere and vice versa in the southern hemisphere. The Coriolis parameter is a function of latitude, but HEC-RAS models are small enough that an average latitude can be used to compute a constant Coriolis parameter for each 2D area. This is known as an F-plane approximation. Coriolis is disabled by default, and for most river and flood simulations, the Coriolis effect is negligible. However, it can be important for large domains or higher latitudes. The Coriolis term is treated slightly differently in the ELM and EM solvers. In the ELM solver, the Coriolis is computed semi-implicitly with a fractional step method. In the first step, a 2x2 matrix is inverted analytically to compute an interim velocity vector V star, which includes the Coriolis. The second step includes all the remaining terms in the momentum equation. The treatment of Coriolis in the EM solver is much simpler. It doesn't use a fractional step method. Instead, the Coriolis is computed explicitly based on the phase tangential velocity. The tangential velocity is computed from a least squares solution of the neighboring face normal velocities. The Coriolis options are set within the RAS unsteady flow analysis editor, which can be opened from the main RAS window by clicking on the button that looks like a stick figure running up a hill. Then from the Options menu, select Computation Options and Tolerances and navigate to the tab called 2D Flow Options. The checkbox at the top that says Use Coriolis Effects turns on Coriolis for all of the 2D areas. The average latitude for each 2D area that is utilized for the Coriolis is on line 15 here. Once you've entered the latitude and checked the box, select OK and save your plan before running. The Coriolis acceleration is only applicable to the shallow water equations. In general, the Coriolis acceleration is relatively inexpensive to compute, even for the fractional step method, so including this term doesn't add much computational time. In addition, the Coriolis acceleration does not introduce a restrictive time step criteria or stability issues. Therefore, if there's any doubt that the Coriolis term should be included, it should be included. But the best way to know if the Coriolis term is important for your dataset is to do a simple test of turning it on and off and comparing the results. Including the Coriolis term only requires the average latitude for each 2D area, so there isn't much user input required. The Coriolis parameter is specific to each plan in 2D area. And finally, if you want to include Coriolis, remember to check the box that says Use Coriolis Effects in the Computation Options and Tolerances editor. All the 2D flow solvers in HEC-RAS require solving a sparse linear system of equations. The method used to solve this system of equations is referred to as the matrix solver. This is actually where most of the computational time is spent, and therefore speeding up the matrix solver, even by a little, can significantly reduce the overall simulation runtime. In general, there are two types of matrix solvers, direct and iterative. Examples of direct solvers are Gauss-Jordan elimination, LU, Cholesky, and QR decompositions. Direct solvers can sometimes be black boxes in that they usually don't require many options and parameters, and so users don't think too much about them. Direct solvers are really accurate but can sometimes fail or be very slow for large, unsteady, or nonlinear problems. Examples of iterative solvers are the Gauss-Seidel successive overrelaxation, conjugate gradient, and generalized minimal residual solvers. Iterative solvers usually have more options and input parameters. And to be effective, they usually require other methods such as preconditioning, matrix balancing, and ordering. And these methods may have their own parameters and options. For these reasons, iterative solvers require more skill and tuning for best results. HEC-RAS supports one direct matrix solver called Partiso. The version in RAS is distributed with the Intel Math kernel library and is based on a version of Partiso from 2006. It uses multiple cores and runs very efficiently, and it's very easy to use. It can be used almost as a black box because as long as you know a few things about the matrix and the right-hand side, it's pretty easy to set up and call. It doesn't require matrix ordering, preconditioning, or anything like that. It handles all of that internally and automatically. HEC-RAS supports two iterative matrix solvers, SOR and FGMRES SOR. SOR stands for successive over-relaxation. This solver is a variation of the Gauss-Seidel solver, but with an over-relaxation factor that speeds up convergence. The parallel implementation in RAS is called asynchronous SOR. The solver and code are extremely simple, so even though it may take more iterations to converge than others, it can still be faster because each iteration is very, very fast. The second option is the FGMRES SOR solver. FGMRES stands for Flexible Generalized Minimal Residual. This flexible variation of GMRES allows for the preconditioner to vary from iteration to iteration. We tried several preconditioners, including some incomplete lower-upper preconditioners, and SOR tended to be the fastest. Depending on the iterative matrix solver, the user may need to specify either 4 or 6 input parameters. The SOR solver has 4 input parameters, and the FGMRES solver has an additional 2. The convergence tolerance determines the overall accuracy of the solver. The minimum iterations increases accuracy, avoids solution drift, and allows the solver to stabilize. The maximum iterations avoid stalling and computing too many iterations when the convergence tolerance is too small. The restart iteration is only applicable to FGMRES. It's not a very sensitive parameter. It can usually be left at around 10. The relaxation factor is used for both the SOR solver and preconditioner. The SOR preconditioner iterations is obviously only applied for the FGMRES solver. A constant number of iterations is used instead of checking for convergence because it's faster and simpler. There are 4 stopping criteria for the iterative solvers. These determine if the solver should continue iterating or if it should stop because it has either converged, stalled, diverged, or reached the maximum number of iterations. The equation for the error estimate is shown on the left. Note the diagonal scaling of the residuals. The error is basically root mean squared of the normalized residuals. For simplicity, the convergence criteria does not include the maximum of the residuals. The matrix solver parameters are set within the RAS unsteady flow analysis editor, which can be opened from the main RAS window by clicking on the button that looks like a stick figure running up a hill. This will open the unsteady flow analysis editor. Then click on the Options menu and select Computation Options and Tolerances. Then navigate to the tab called 2D Flow Options. The matrix solver parameters begin on line 17. Adjust the parameters as needed and click OK and save the plan before running. The UK Environmental Agency released a report in 2013 with benchmark test cases for 2D hydraulic models. This example is test case number 5 of that report. It's a flooding simulation of a river valley about 17 kilometers long and 1 kilometer wide. The animation on the top left shows the flooding simulation in RAS. The test case was run in RAS with the 3 available matrix solvers. The table on the right shows the parameters for the iterative solvers. The bar plot on the lower right shows the runtimes with the 3 solvers. Compared to Partiso, the FGMRES and SOR solvers had speedup factors of about 125 and 160% respectively. These were all run with 8 cores. The plot on the lower left shows a comparison of water levels at a point downstream and demonstrates that the 3 solvers produced essentially the same result. The iterative solver parameters were not calibrated but simply estimated based on the recommended range and experience. so they could be optimized further to get even faster runtimes. When setting up a model, it's recommended to start with Partiso. This is so that you have a reference to compare the iterative solver results and runtimes. Ensure the model is stable and running well. This means not going to max iterations every time step and reporting large water surface or volume errors. Once the model is running well, try the iterative solvers starting with HEC-RAS. Start with conservative parameters. This means small convergence tolerances and lots of iterations. Compare the iterative solver results to Partiso to make sure there's no solution drift. If there is, then the convergence tolerance may be too large, the maximum number of iterations may be too large, or the minimum number of iterations may be too small. Adjust the parameters to optimize the runtime. This means increasing the convergence tolerance, reducing the number of iterations, and increasing the relaxation factor. One useful tip is that any iteration parameters left empty or set to 0 are automatically computed based on the mesh size. This can be useful for getting initial estimates of these parameters. And with that, thank you for watching. For HEC-RAS downloads, documentation, and other things, please visit the HEC-RAS website shown here. The latest online documentation can be found on the Confluence website shown here.